Physics, waves are have an interesting position because they occur everywhere in physics, and yet waves have nothing to do with physical law per se. Waves are the consequence of physical laws, but we don't have physical laws in classical physics that actually say what waves do or don't do, or what is a wave. I am a classical physicist, which means I don't do quantum mechanics. I do electricity and magnetism, and I do mechanics and things like that. And in classical physics, just like politics, all physics is local. And that means that if you're a piece of something, the only thing you know about the world is what's going on next to you. If you're a piece of water, you don't know about any wave out there anywhere. If you're a piece of air, you don't know about somebody talking somewhere, making a lot of noise. You just pay attention to what the guy next to you is doing, and you satisfy the local physical laws. The wave is always a phenomenon which is a consequence of the local rules of behavior, okay? And so what makes waves so cool is that they appear everywhere in physics, but they're always related to that ultimate question: what are the local rules that give the wave in the first place? Now we're going to talk about water, all right? Let's move on. And if we're talking about water and waterways, the first thing you can do is you can ask yourself, can we learn anything about the wave just from looking at the forces? And I've written down 4 forces: pressure, viscosity, surface tension, and gravity. Okay, pressure is easy. It's the force of the guy next to you pushing against you. That's all there is to it. Okay. Viscosity is if you have shearing action, and it's a kind of a friction. Viscosity is very important in fluid mechanics, extremely important, but it generally acts on very tiny scale lengths. Very rapid phenomena happening at very small levels. We're going to forget about viscosity. We're allowed to do that because we'll say, we are in the high Reynolds number regime. Thank you very much. And the high Reynolds number regime means we forget about viscosity. Surface tension is a real neat one, and it's a lecture that I'd love to give, and I'm not going to give you guys. But basically, surface tension is energy per unit area. And if you pick up water and lift it and carry it around, that's energy per unit volume. Combine those things together, and you say, well, don't take the score. We end up with a characteristic length, below which surface tension is really more important than gravity, and above which gravity is more important than surface tension. And that size scale is about a centimeter. So if you're an insect, and you're living on the centimeter and below size scale, surface tension is probably a lot more important in your life than gravity. You can climb up walls, and if you get wet, you can't fly, right? For us guys, we forget about surface tension, we forget about the pools. But you do have waves associated with surface tension on the surface of a liquid, and that's called ripples. And they have wavelengths of about a centimeter or below. Okay? We're not doing ripples today. So that leaves us with pressure and gravity, and everybody knows what gravity is, okay? Spooky added, Newton said gravity's action at a distance, right? And I said everything's local. Well, fortunately, Einstein came around and said, no, it's just curvature of space-time, and that's local too, so I can get away with that. So, here we are in the liquid, and we have pressure. Now, one thing we can do in the liquid, just like in air, we can have sound waves. And those waves are driven by pressure, and then you have the elasticity of the medium comes into play. You compress the medium, and it pushes back, and you have pressure waves, and you can have sound waves in air and water and everything. For the water waves we're talking about, which are surface waves, we'll treat the medium as incompressible, okay? Very low frequencies. Okay, so even though you could say sound waves are example of water waves, they are, we're talking about waves that occur at an interface. In water, there are various scales, and I've already talked about the scale for ripples. At the larger scale, there really isn't much going on. Look, I can have a wavelength. Think of waves on the ocean have so distance apart, and I can ask, is that wavelength smaller or larger compared to the depth of the water? In the short wavelength limit, we call that the deep water case. If the water is so deep that the wave doesn't get down to the bottom, it doesn't know it's there. And so the only thing that plays a role in the propagation of the wave is the wavelength itself. And what this view graph is saying is that the velocity of the wave depends on the square root of the gravitational constant g, which you all knew because you all took physics, and the wavelength. Okay? G is the acceleration of gravity, centimeters per second squared, and lambda is the wavelength. We call that centimeters. Take the square root of that, you get something with the dimensions of velocity. What's missing in this expression? What's missing is the water. Look, there's nothing about this that says this is a wave in water. It's just the wavelength, and g, which is 9.8 meters per second squared. Okay, well, Galilean knew all about that. You drop a mass, the acceleration is independent of the mass. The guy with the pendulum, the period of the pendulum depends on the length of the pendulum, but not the mass. So the mass cancels out, and if this were a wave in a sea of mercury, it would have the same propagation speed for the same wavelength. Okay? Now, that's because the wavelength is short compared to the depth. In another limit, I'll skip that one. In another limit, we have the shallow wave limit, where the wavelength is longer than the depth. Okay? And in this case, the velocity depends on g times the square root of the depth, and it's independent of the wavelength. Okay? So what? So what is that if I look at these little waves that are going out there now, those are short wavelength waves and those are deep water waves. When we get the whole swimming pool going back and forth, we'll be going to look at about half a wavelength of a shallow water wave. Okay? So it's a little different from that regard. But there's a lot that can be gotten out of this formula, or the previous one too. I'll just try this one. Supposing the depth were a kilometer, like you're out in the ocean, so d would be 1,000, and g is 10 meters per second squared. Take the square root of that, you get a velocity of 100 meters per second. Well, that's over 200 miles an hour. Okay, now this is the neat thing about water waves, is they're scale independent once you get above the scale of ripples. So this is really true. It's not just true for swimming pools, it's true for the ocean. You can have very long waves going at hundreds of miles an hour. You know, you hear about these when there's an earthquake somewhere and when it's going to hit California. When we talk about wavelength and things like that, we are in what is called the linear regime. Now, people who've gone on in physics or mathematics know exactly what the linear regime means. What we're talking about is originally, whether it be air with sound waves or water waves, you have some kind of median or equilibrium situation that you're going to perturb. And the wave represents the propagation of that perturbation from one place to another. In the case of the water waves, again, the rules of physics, I could have said this earlier, are conservation of water, which means if I push the water together, it's got to go up in the swimming pool, and Newton's law of F equals ma, which is if I push harder on this side than on this side, the water is going to accelerate in that direction. That's the only physics we put in here. But in the linear regime, we get these nice relations about wavelength and depth. By linear, I mean that the amplitude of the wave is small compared to everything else. Small compared to the wavelength, small compared to the depth, and so on. Well, if we look at this formula again for the shallow water wave, real quick, you can almost see from the drawing that I made that there's a problem here. The velocity depends on the depth, but in the way I've drawn it here, it's deeper here than it is over there, right? So these crests, where these crests are, the wave velocity should be faster than it is where these troughs are, where it should be going slower. And that can only mean one thing. It means that the wave is going to form a breaker. Okay. So what happens in the ocean? Nice linear waves come in. Their amplitudes are so much that the water is so deep that we're in the linear regime. When we come up onto the shore, suddenly the wavelength is becoming comparable to the depth. Things, as the water gets more shallow, the waves go slower, the amplitudes get bigger, everything gets nonlinear, and this happens. Okay, now there's some other words that go with linear and nonlinear. Linear waves are waves, mean the waves add up. If I'm talking and he's talking, you can hear both of us because the pressure variations caused by our voices are much, much less than atmospheric pressure. And so those sound waves are in the linear regime, and those waves just add to each other and go pass right through, no problem. And those waves are reversible in the sense that they basically leave the medium in the same state after they passed as it was in when they started. In the nonlinear case, the waves are irreversible. You're not going to be able to run the movie backwards on a breaking wave and convince anybody they're seeing real physics, I think. When I was at the lab, I said I worked with underground nuclear testing and shock waves, and this picture, which is just a kind of a step function, is what a shock wave looks like. Imagine that on the, what is your left side of the picture, so on the right side of the picture, you have atmospheric pressure. And on this side, you have the pressure of a huge pressure wave that's coming in several times atmosphere. Okay? Well, again, under these circumstances, this air is heated. You have a situation where the wave velocity behind the shock front is faster than the shock front itself. And interestingly enough, the shock front is moving faster than the wave velocity in front. So the shock front goes faster than the speed of sound, but everything behind the shock front moves into the shock front. Does this look a bit like a tsunami after it's kind of shorter? It ought to, because a tsunami, and you have these terrible pictures from Japan that you certainly won't forget. Tsunami is just that, it's a shock wave. And a shock wave is irreversible, and the best way I have to describe a shock wave is on one side, nothing's going on, nobody knows what's coming. On the other side, all hell's broken loose, and it happens very quickly. Now let's talk about what we're going to do here. In nature, you know, I talk about wavelengths and things like that, but in nature, wavelengths don't just happen. In fact, physicists kind of invented frequencies and wavelengths to make their lives easier. But when you confine a wave to boundaries, then you do get resonant frequencies. So the picture I'm showing you here is a picture of a slosh mode in a swimming pool. Okay, like this, and it has a definite period, which, just like our velocity equation, is independent of the water. Again, the cycle time is independent of the density. We could do this swimming pool full of water, full of mercury, we would have the same period. Okay, so what we're going to do is we're going to drive the swimming pool at its resonant frequency. And the first question is, well, Mr. Wright, I noticed that your formula had a depth for the pool, and this pool doesn't have a constant depth, so what number do you put in for that? And I answer, I'm a full-time accredited physicist and I know how to do those things. So what you can do is use all the different equations and hope for the best. We have designed the pendulum of destiny so that its period is 1/4 of what we think the period of the swimming pool is going to be. We're not sure. We're going to find out, okay? You guys are going to find out. So what you're going to do is you're going to drive it resonantly to get the energy in. And to demonstrate how you do that, I got to borrow the pendulum back from there. Anyway, here's the pendulum. It's got a resonant frequency. And how do we get it going? Okay, there it is. Well, remember, the wave represents energy. So forget about forces and things and say, how do we get energy into this mechanical system? Well, here I am. Okay, the forces are equal and opposite, but I'm pumping energy from my right hand into my left hand because I'm moving in the direction of the left hand. If I do this, the energy goes the other way. You say, oh, well, I don't believe that. Well, because energy wasn't conserved in that demonstration. But, you know, the pendulum kind of conserves energy. So if you push the pendulum in the direction it's going, You'll always be putting energy into the pendulum. That's all, and that's how you get the swing started, right? Okay, so that's, okay. So what we're going to do is we're going to put energy into the swimming pool in the direction of the force. When you get in the water, the swimming pool is pushing up on you, and you know, and the buoyant force, guys, and you are pushing down on the water, equal and opposite, okay? So, if the water is going down, and you're in the water, you're pushing on the water, down. You're not doing anything, you're just floating there, but the water is going down and you're pushing on it. Okay. Now, when the water comes up again, it does the work back on you, and it's a, you're even. But if you're not in the water, the energy doesn't come back out. So what's the rule? Very simple. Go in when the water is high, get out when the water is low. It's just the opposite of doing the stock market. In when the water is high, out when the water is low. We're going to go in and out with the pendulum. Eventually, we hope to see the water doing this, okay? And then we don't need the pendulum anymore. Okay, so how we're going to do this, our volunteers are going to line up here, and I guess I'm going to be one of them. Jim is going to operate the pendulum of destiny. When he says in, we're going to go in. Now, when you go in up to your neck, because the more of you get in the water, the better you're doing. More buoyant force. When you get out, you try to get out as much as you can. That's not going to be easy, and I'm serious about that. If you cannot get out, don't get out until the next cycle. These guys are my rubber duckies that have got little drag strips, and what they're doing is they're going to sit out there in the middle. I'm going to put them out in a moment, and they're going to give us the horizontal motion. The horizontal motion is actually quite larger than the vertical motion at the end. So we hope that we'll be able to see the horizontal motion building up out there. If we are lucky enough to get the water coming up over the edge here, we'll stop and everybody can swim out to where the duckies are and go back and forth. How's that sound?
On your marks. In.